Hello everybody. In this video, we are going to prepare ourselves for some of the integration properties by stepping back. We know that our upper and lower integrals are defined in terms of upper and lower sums. Our upper and lower sums are defined in terms of suprema and infima. So it will be helpful to have some more properties about suprema and infima. And so I'm going to list off some properties in this video and maybe prove some of them, leave a bunch as exercises for the reader. Hopefully I give you enough detail so you can do that. All right, so we are going to state the supremum and infimum omnibus theorem. Okay, so we've had several omnibus theorems this semester. Just collect a whole lot of useful results here. So our assumption or assumptions are going to be, all right, we have two subsets, A and B, of the real numbers. We have some real number C. And then I'm going to have a couple of functions whose domain is A. No interesting assumptions about F and G. They're just functions. All right, so the first statement is that if A is a subset of B, then the supremum of A is less than or equal to the supremum of B. Okay, so this is not going to be super complicated. So we're going to prove these as we go, in fact, because this is going to be fairly long. All right, we're going to have 10 different statements. So I'm just going to prove them as I go. So this first one, let's say I have some element A and A. Well, because A is a subset of B, then of course we know that A is an element of B. Okay, but what does this tell you? If A is an element of B, then A is bounded by the supremum of B. So then A is less than or equal to the supremum of B. And what this tells you then is that the supremum of B is greater than or equal to every element of A. So the supremum of B is an upper bound for set A. Okay, but the supremum of A is the least upper bound. So if I know I have another upper bound, that other upper bound must be at least as big as the supremum of A. So that means that the supremum of A is less than or equal to the supremum of B because this is an upper bound. Okay, and that's the proof. Nice. All right, so the second statement will be the version of statement one for the infimum, and I'm not going to prove that one, right? I'll let you do this one. So if A is a subset of B, then the infimum, well, this time of B is going to be less than or equal to the infimum of A. So I'll let you play around with it. The argument is essentially what we did in number one. All right, number three. If I take the supremum of the sum of the sets A and B, so just on the side, recall, if I add two subsets of R, I just mean look at all possible sums where one summand is from the first set and the other summand is from the second set. So if I take this set, A plus B, and I look at the supremum, it will be precisely the sum of the suprema of A and B. So we'll prove that. So this one will be a little more involved than our proof of number one. All right, so one direction is reasonably straightforward. The other one has a little bit of a tricky argument to it. So first, if I have elements A and B and B, well, then of course I know that A is less than or equal to the supremum of A, and B is less than or equal to the supremum of B. Okay, but this implies then that if I add A and B together, that will be less than or equal to the sum of the suprema of A and B. So this tells me that the sum of the suprema is an upper bound on the set A plus B. So sup of A plus sup of B is an upper bound for A plus B. Okay, but that means if it's an upper bound, then it must be at least as big as the least upper bound. So that tells you that the supremum of A plus B is less than or equal to the sum of the suprema of A and B. All right, so we've shown that the left-hand side is less than or equal to the right-hand side. So now we need to turn around and show the reverse inequality. All right, so this is where we need to get a little bit clever. All right, whoops, there we go. Okay, so now going the other way, so if we fix, say, some A in A, okay, then the supremum of A plus B, of course, is going to be at least as big as A plus B for all B and B. Okay, so A here is just some fixed element in A, and now I let B go through all elements in big B. And of course, the supremum of A plus B will be at least as big as all of those elements. All right. Now, if I subtract the A to the other side, then I know that the supremum of A plus B minus A is at least B. Again, this is for all B and B. And so that tells me that the supremum of A plus B minus this fixed element A is an upper bound for the set B, all right? Because this is at least little b for all B. So the supremum of A plus B minus A is an upper bound for B. But if it's an upper bound, then it must be at least as big as the supremum. So this tells me that the supremum of A plus B minus A is at least as big as the supremum for B. Okay, so this was true though for all A and A, right? I fixed one of them, right? But this is true for all A and A. So let me swap things around here. And I'll get that the supremum of A plus B minus the supremum of B is at least as big as A, but now this is true for all A and A. So again, we get that the supremum of A plus B minus the supremum of B is an upper bound. Which time, for which set this time? Well, for A. But again, if it's an upper bound for A, then it must be greater than or equal to the supremum for A. So the supremum of A plus B minus the supremum of B is at least the supremum of A. And now we just move the supremum of B over to the right, and we get that the supremum of A plus B is at least as big as the sum of the suprema for A and B. Okay, so let's check. Let's see. We have supremum of A plus B is at least as big as the sum of the suprema, and we have that the supremum of A plus B is no bigger than the sum of the suprema. Therefore, the supremum of A plus B is equal to the sum of the suprema of A and B. Whew, okay, we did it. So we're able to prove number 3. All right, let's get to number 4. So number 4 is going to be the equivalent statement for infima. We won't prove it. The argument is going to be reasonably similar. So the infimum of A plus B is the sum of the infima of A and B. All right, let's move on then to number 5. So for number 5, I would like to be able to convert back and forth between suprema and infima. And so the way we're going to do that is by saying, well, the supremum of a set A is equal to what we get if I take, well, first, I'm going to start with the set negative A. So what do I mean by that? Negative A will just be, you just take every element in A and put a negative in front of it. And that'll be the set negative A. I take the infimum of negative A, and then I'm going to negate that infimum. And that will give me back the supremum. All right, so let's give a proof of that a try. So we'll prove this. So again, let's start with some A and A. I know that, of course, A is bounded by the supremum of A. Okay, but if I negate everything, that will reverse the inequality. So if I multiply by -1, negative A will be at least as big as the negative of the supremum of A. But this negative A here, right, that's giving me now an element of the set negative A. In fact, every element of the set negative A is the negative of some element in A. So what this tells me is that the negative of the supremum is a lower bound for negative A. So the negative of the supremum of A is a lower bound for negative A. But if you're a lower bound for a set, then you are less than or equal to the infimum of that set. So negative the supremum of A is less than or equal to the infimum of negative A. Or if we multiply by -1, then we get that the supremum of A is at least as big as negative the infimum of negative A. I'm trying to show that the supremum is equal to the negative of the infimum of negative A, and I've shown here that it's at least greater than or equal to. So now all I have to do is show the reverse inequality. Okay, so for the reverse inequality, well, this negative A here, that's an element of the set negative A. And so it's at least as big as the infimum of the set negative A. Whoops, the infimum of the set negative A. Okay, again, multiply by -1. Then I'll get that A is less than or equal to the negative of the infimum of negative A. But this tells me that the negative of the infimum of negative A is at least A for all A and A, so this is an upper bound for the set A. So negative of the infimum of negative A is an upper bound for A. But if you're an upper bound, then you're at least as big as the supremum. So the negative of the infimum of negative A is at least the supremum of A. And so we've now shown that the supremum is at least as big as the negative of the infimum of negative A, and that it is also less than or equal to the negative of the infimum of negative A. All right, so we conclude sup of A equals negative inf of negative A. And there's the proof of 5. All right, now number 6, just the same sort of statement for the infimum. The infimum of A is the negative of the supremum of negative A. I leave that to you. You can actually prove this. Well, you could do it directly as we did in the proof of 5, but you could also just use the result of 5 to prove this. All right, how about we go to number 7? So in number 7, we're going to, in a sense, generalize what we did in 5. I want to now not just be able to multiply, say, my set A by -1. I'd like to be able to multiply by any constant. So let's say I wanted to know the supremum of C times A for any constant. So it turns out it's going to depend on the sign of C. So if C is greater than or equal to 0, then I'm just going to get C times the supremum of A. But as you might expect from 5 and 6, if I multiply by a negative number, this supremum is going to turn into an infimum. So I'll end up with C times the infimum of A. Okay, so let's see if we can prove this. Fine. So, well, the first case we'll handle is just the C is equal to 0. Okay, this is going to be an easy case. So if C equals 0, then, well, the sup of CA, right, this is, of course, just the 0 set. So the sup is 0. And of course, that's the same thing as if I did 0 or C, whatever, times the sup of A. Right? 0 times sup is 0. So no problem there. Okay, so what if C is positive? All right. If C is positive, well, let's see. What if A was an element of A? Then, as before, we know that A is less than or equal to the supremum of A. So now let me multiply by this positive number C. So if I multiply by C, then I get that AC is less than or equal to C times the supremum of A. Okay, but this tells me now that C times the supremum of A is at least as big as, in fact, here, let me write the C in the front, see if that helps. This means C times the supremum of A is at least as big as C times every element in A. So this is, again, an upper bound for the set CA. So C times the sup of A is an upper bound for C times A. Okay, which, by the way, in case it's not clear, right, C times A just means you multiply everything in A by C. Okay, so C times the sup of A is an upper bound. Well, that means that it must be at least as big as the supremum. So C times the sup of A is at least as big as the supremum of CA, excuse me. Okay, because it's an upper bound for CA. All right, so we've shown one inequality, right? Now we're going to have to show the other direction. All right, well, this is a little trickier. So the sup of CA, that is, of course, an upper bound for CA. So this is an upper bound for the set CA. Okay, now C is positive, and so if I divide everything I see by C, so I take supremum of CA and divide it by C, and the CA here and divide it by C, I'm not going to change the inequality, right? I would have sup of CA is greater than or equal to everything in the set CA, so dividing by C doesn't change the direction of that inequality. So this implies that 1 over C times the supremum of CA is an upper bound for 1 over C times CA. But 1 over C times CA, that just means I take everything in A, multiply it by C, and then multiply it by 1 over C, which is like I didn't really do anything at all. So this is just the set A. Okay, so 1 over C times the supremum of CA is an upper bound for A, which means that 1 over C times the supremum of CA must be at least as big as the supremum of A. Well, now let's multiply by C. Now I know that the supremum of CA is at least as big as C times the supremum of A. Well, look at this. On one hand, I knew that C times the supremum was at least as big as the supremum of CA, and on the other hand, I know that C times the supremum is less than or equal to the supremum of CA. Therefore, the supremum of CA is equal to C times the supremum of A. All right, so that handles the second case. We know what happens when C is 0. We know what happens when C is positive. So one case left, and that's if C is negative. Okay, well, we are going to use what we already know. So if C is negative, this implies that negative C is positive. So now, if I take the supremum of C times A, I can rewrite this as the supremum of negative C times negative A. Okay, so negative A, remember, I just take everything in A and multiply it by negative 1. So now I have all these negative A's. Well, I multiply them by negative C's, and I get exactly my CA's back, right? So I'm getting exactly this set. Okay, but negative C is positive, and we just showed that if you have a positive constant, you can simply pull it out of the supremum. So this is equal to negative C times the supremum of negative a. But let's go back up. If I have the supremum of negative a, well, by 6, okay, you just move this minus over. So this is equivalent to saying that the negative of the infimum of a is equal to the supremum of negative a. So I can replace the supremum of negative a with the negative of the infimum of a. So I come down here, I have the supremum of negative a. This is the negative of the infimum of a, all right? This is by 6. Okay, well, I have a negative c and a negative inf of a. The negatives go away, and I have c times the infimum of a. And that finishes the proof of 7. All right. Number 8 is going to be essentially the same sort of result as number 7, but again, for the infimum, and I will leave that as an exercise to the reader. So the infimum of c times a is going to equal c times the infimum of a when c is non-negative, and it will equal c times the supremum of a when c is negative. Okay, how about number 9? Well, we haven't used the functions that we started with. At the very beginning, we had 2 functions, f and g, whose domain was this set A. So we're going to finish by writing down 2 results about f and g. So what I want to do is look at what I'm going to call the supremum of the sum of f and g. So what I mean by that is, well, first, let me tell you, if I have the supremum of a function, what I really mean by that is I apply f to the domain. That gives me the range, right? So this is the range of f. Well, the range of f has a supremum, and that's what I'm going to call the supremum of a function. It will just be the supremum of the range of the function. So when I have the supremum of f plus g, I mean the supremum of the range of f plus g. And the claim is that there's a relationship between the supremum of f plus g and the sum of the suprema of f plus g, of f and g. But it's not an equality, which is what you might expect from earlier in the omnibus, right? When we said, oh, if you have the supremum of a sum of sets, it will be the sum of the suprema. But here we need to be a little more careful, and we'll see why in a second. The answer is, well, they are related, but not equality typically. It's going to be a less than or equal to. Okay, so we'll prove this, and we'll write down a version for the infimum. So let's see here. Proof. Okay, so first thing, what is the range, right? So, well, I have to apply f plus g to the set A. And what this is going to be is all the things of the form f of a plus g of a, where a runs through all the elements in A. Okay. Note that the A here, these are the same A, right? I'm applying f plus g to a particular A, which just means I apply f to A and I apply g to A and I add those. And this is going to be a subset of the set that I would get if I looked at things of the form f of x plus g of y, where here, again, x and y are in A, but they don't have to be the same element. Okay, so this is the big difference. This is why we're going to get this less than or equal to rather than an equality. Is on one hand, I have a set of elements that just look at f of a and g of a and add those, versus f of something plus g of maybe something else, and look at all those possible sums. And so there's going to be a lot more elements in this second set typically. Okay. Of course, this set here, I could write it actually as a sum of sets. I say, okay, look at the set of all f of x, where x is in A. Look at the set of all g of y, where y is in A. And then look at the sum of those sets, which again means you just look at all possible sums from with one element from each set. Okay. Okay, so once we have this, I now know that I have a set, f plus g of a, which is a subset of another set, in this case even a sum of sets. And our very first part of the omnibus theorem said, if you have a subset, then you know that the suprema get bigger. That's where this less than or equal to is going to come from. So the supremum of f plus g, well, that's just the supremum of the range. That's this f plus g applied to A. This is equal to the supremum of this big set, right? F of A plus G of A for all A and A. But because this set up here is a subset of the one down below, and I can even use the one on the bottom, this is less than or equal to the supremum of the set of all f of x's, where x is in A, plus the set of all g of y's, where y is in A. Okay, but now I have a sup of a sum of sets. And if we go back up to number 3 rather, we know that the supremum of a sum of sets is the sum of the suprema of the sets. And so this is equal to the sup of the set of all f of x, x in A, plus the sup of the set of all g of y, where y is in A. But the sup of all the f of x's, right? This is the range, okay? This is the range of f, and this over here is the range of g, right? And so this is equal to the sup of f plus the sup of g. And there we go. We've shown the sup of f plus g is less than or equal to the sum of the sups of f and g. All right. So our final statement, number 10, will be about infima, and they're going to be basically the same idea, only their inequality will go the other direction. So the infimum of f plus g will be greater than or equal to the infima of f plus the infimum of g. And as you might expect, the reason why the inequality goes in the other direction goes all the way back up to number 2, where we showed if you had a subset, the infimum of the larger set will be less than or equal to the infimum of the subset. And there we go. All right, this is not the end of the story with suprema and infima. There's lots of interesting relationships one can write down, but these are particular ones that we're going to want as we go into proofs of the properties of integrals. Okay, everybody, next time I think we'll probably get into a little more preparation for those integrals, but they're coming very soon. We'll see you then.